our last topic in this section is binary liquid mixtures. So it is still a solution, but since both of the components started out as a liquid, we have to consider the vapor pressure of both parts. So basically for this section, we're only going to worry about vapor pressure over the solution. It's just going to be a little bit more involved than when we did the vapor pressure of other solutions. So the summary is that the vapor pressure of both components matters. And if you look at this picture, so I have some solution. I've used some orange X's and blue O's to show the different components in the solution. So one is some liquid, the other is some other liquid that we've mixed together. And each will have its own vapor pressure over the solution. And it's going to depend on the same stuff that we saw before. So whatever its normal pure vapor pressure is, and its mole fraction in the solution. So I'm going to put in some vapor molecules, right? So I'll have some part of the vapor that's made up of vapor molecules of whatever liquid X was, and I'll have some part of the vapor that's made up of vapor molecules of whatever the O liquid was. So we will use Raoult's law. So separately, if we think about it, the vapor pressure due to, I guess let's do the X's first, liquid X, will be the mole fraction of X in the liquid times the pure vapor pressure of X. And the pressure over the solution from O will be the mole fraction of O in the liquid times the pure vapor pressure of O. Okay, so maybe O wasn't the greatest choice with the circles, but hopefully this feels okay to you. So each one has its own contribution to the vapor pressure. Now, something that we haven't used in a while, but still applies in this case, is Dalton's law of partial pressures. So Dalton's law of partial pressures says that if I want to know the total pressure, all I have to do is add up the pressure of these individual components. So the total vapor pressure over the solution will be the pressure from X plus the pressure from O. So all of these relationships together will let us determine different pieces of information about the solution. So to go along with these equations, I have a little bit in terms of words or bullet points that we can look at. So some things that we have already said, which is that each liquid has its own vapor pressure, which is that P with the superscript, O circle, that contributes to the total vapor pressure. Which is our P total based on its mole fraction in the liquid. So that would be the chi with the superscript LIQ to indicate that it's in the liquid. And we're going to need to keep that superscript because we will often need to look at the mole fraction in the vapor, and so we need a way to designate those. Now, the reason that we need to do that is that a more volatile liquid so remember this term came up when we were talking about intermolecular forces. So volatile just means that it evaporates easily. So you could imagine, if we try to put that in terms of what we're going to look at in this section, it means that it has a higher vapor pressure just as a pure vapor pressure. So this more volatile liquid will contribute more to the vapor pressure over the solution. And that's because this P0 is higher. So what we will find is that its mole fraction in the vapor is not equal to its mole fraction in the liquid. Okay, so I think the best way to look at the different pieces of this is with an example problem. So I'm going to pause this, get the problem written out, and then we will do some calculations. The example that we're going to look at says that we have a mixture with 50 grams of ethanol and 50 grams of water, and then it gives the molar masses for each of those, but if you needed to, you could calculate those as long as you had the formula for ethanol. And we need to find the vapor pressure over the solution, and we have the pure vapor pressure of water and the pure vapor pressure of ethanol. So we need to figure out the pressure for each of them and then add them up to get the total pressure, right? Because it says the vapor pressure over the solution, so it wants both of the components added up. So to get my pressure of water, I need the chi of water and the pure, I need chi of water in the liquid and the pure vapor pressure of water. And for ethanol, I need the chi in the liquid for ethanol and the pure vapor pressure for ethanol, and then I will just add those two things together once I have them. So mole fractions for each is where we need to start. So honestly, moles for each is where we need to start, and this would be a good place for you to pause the video if you need practice with mole calculations to make sure that you end up in the right place. You should get that there are 2.775 moles of water and there are 1.085 moles of ethanol. So for mole fractions, my mole fraction in the liquid for H2O is moles of H2O divided by the total, so 2.775 plus 1.085. So my mole fraction of water in the liquid comes out to 0.719. And my mole fraction of ethanol in the liquid, now it's moles of ethanol divided by the total. So this comes out to 0.281, or if you look at all of the things that we're including, we have two components in our solution. These mole fractions are just a percentage of composition. We just haven't multiplied by 100. So my two mole fractions here should add up to 1. If I had 3 components, then the mole fraction for all 3 components should add up to 1. So this second calculation, whichever one you happen to do second, you can do it in any order, I should be able to do 1 minus the mole fraction in the liquid of water to get the mole fraction in the liquid of ethanol. And if I do that, 1 minus 0.719 equals 0.281. So this works. Now I bring this up to help you make your calculations go a little more quickly, and also because you will need in some problems to use this equation that I've highlighted as, say, a second equation, because you have to solve for 2 unknowns. You can't see me winking at you to give you a hint, but that's a really big hint that this is going to come up later and you're going to need it. Now, we don't necessarily need it for this one, but we now have 2 parts of what we need to include in our calculation to get the total vapor pressure. So my pressure over solution for the water is the mole fraction of water, which is 0.719, times the pure vapor pressure, which is 23.712. And this gives me 17.05 torr. My pressure of ethanol is 0.281. My pure vapor pressure is 59.28. And so my pressure over solution of ethanol is 16.66, which means that my total is just the sum of those, which is 33.71 torr. Now, something that you can see here is that the vapor pressure of ethanol over the solution, the 16.66, that's almost as high as the vapor pressure for water, but their mole fractions are drastically different, and this is just because the ethanol is much more volatile, which you can see from its pure vapor pressure, than the water was. So this is why when we continue on in a little bit to look at the vapor pressure, or not the vapor pressure, the mole fraction of ethanol in the vapor, it's not going to match what the mole fraction was in the liquid. Okay. So this is, let me put a box, this was our final answer. Just asked us for the pressure over the solution. So let's do the mole fraction in the vapor for each component. And what's really nice is that we will be able to use the pressure values that we already have to do this calculation. So if we take Raoult's law and apply it to what's happening in the vapor, the pressure of water in the vapor is going to be chi vapor of the water times the total pressure. Well, actually, technically, this is part of Dalton's law, not Raoult's law, since we're talking about everything in the gas phase. And then Dalton's law with the ethanol, chi vapor of the ethanol times the total. So we definitely did this when we talked about gas laws. If you have questions about these equations, you should definitely let me know. These equations, if we rearrange them, we can get the mole fraction in the vapor by doing the partial pressure divided by the total pressure. So, and again, these are going to add up to 1, so we only have to do it for the first one. But the mole fraction of ethanol in the vapor is the partial pressure of ethanol over P total. So for water, This is 17.05 for 33.71, and that's 0.506 for ethanol, 16.66, 33.71, 0.494. So even though water made up a bigger mole fraction of the liquid, because it is so much less volatile than the ethanol, the mole fraction in the vapor is much different. And our partial pressures were pretty close to each other, so these mole fractions are actually pretty close to each other.